yesterday we were trying to understand the concept of fatigue for tubular joints. I think in the previous few classes we have already understood how the joint is designed for static loads. There are several methods I think were deliberated for the design of tubular joints for cyclic loads. One of the simplest and the methodology which has become obsolete now, but of course still recommended for preliminary studies, is the simplified fatigue evaluation without looking into the cyclic the loads are repeated. So, basically it is very similar to the punching shear check or the capacity check which we are making for joint design for static loads. Only thing is we are just looking at slightly modified method, that means here the number of cycles will not come into picture. So, in this method we will do a design C state instead of taking this the various C conditions exist for the design life. For example, if you take 25 years, you will see different C states going to exist for different period of time and number of cycles for each of the C state will be different. Instead of going and looking at those data, API initially 1960s early stage have recommended pick up a C state which will be representative of the overall behavior of the C state conditions at the particular site and analyze the structure very similar to the in service analysis like a storm condition, and calculate the applied axial stress, bending stress and the in plane out of plane components, calculate the stress concentration factors which we will be dealing with it in more detail later on. Stress concentration factor is the ratio of the local stress to the nominal stress, and then find out the combined effect of axial plus bending including the concentration factors. Basically this is the SRSS value of your in plane out of plane because it is a circular shape, and before you do the SRSS you multiply the corresponding stress concentration factor. That means in plane stress multiplied by in plane stress concentration factor square, and basically the same thing to the out of plane, and then you take the value of axial stress just like a nominal normal combination what we used to make, axial stress plus the bending in plane and bending out of plane, because all these stresses are acting in the same direction, no. So, basically you combine them, find out the combined peak or the combined highest hotspot stress. Once you have this, this is the applied stress due to a representative C state which represents the fatigue waves during the lifetime. It could be 20 years, 30 years, 50 years, and then compare this with a allowable hotspot stress, very similar to what we are doing for a static design. What we did there is applied axial load, applied bending moment, and then we had a allowable axial load and allowable bending moment, and as long as the allowable is higher we decided that the joint is safe against static load. So, the whole procedure here is the catch is the first one which is the design representative C state, the last one how do we get the allowable hotspot stress. Otherwise, the procedure is as usual as computing the stresses in the member. Instead of that we are doing the stresses in the member multiplied by the local increase due to the stress concentration, and then you combine them. So, procedure is exactly same. We need to find out what is the design C state and what is the allowable. So, API have initially recommended you take 100-year storm condition which will be the maximum wave height for that particular site and take as a representative value, and basically use that to study the member stresses and local hotspot stress. So, when we are doing the in service condition we do exactly the same, except that we will not multiply the stresses by stress concentration factor. We will be taking only the nominal stress to check the members, whereas here are going to take the local hotspot stress to check the joints, and then the allowable peak hotspot stress is just a comparison. That means this needs to be provided by somehow, either by empirical formulas or by some recommendations. API has given a initial charts like this. You could see here the horizontal axis is the water depth and the vertical axis is the allowable hotspot stress in KSI, I think. So, basically you can see most of them are larger than 30-40 KSI, that means is nearly higher than the yield. You know, high strength steel is 50 KSI, no, I think most of you remember. So, you could see here for 100 years and slightly reduced design life, API has recommended. This is again based on Gulf of Mexico studies. All these recommendations given in API, remember all of them are only I would say 100% applicable to Gulf of Mexico. You could apply if you read the API preface, they will say you should apply your local conditions before applying API requirements to anywhere else, because the codes are developed only for their region of the interest, whereas when you apply to Indian waters or elsewhere, you need to make sure that the parameters that you are looking at are similar, or at least you are aware of the things that they have done. So, this particular chart is basically applicable to Gulf of Mexico area. So, the water depth is given in terms of so many feet. So, as long as you see here you are within this 400 meters water depth, 400 feet water depth, you could apply this idea, but if it is larger, then you can't apply this particular graph. And basically for 100 year, the dotted line, I think as all of you can see, if it is for example 100 meter water depth, your allowable peak hotspot stress is around 48 KSI, which is very close to yield 50 KSI material. And basically for reduced lifetime period. So, you can see here the design fatigue life is 40 years, then the allowable high stress is going slightly higher. So, these two graphs, there are level 1 and level 2. What is level 1? Level 2 is basically the risk level, like we were trying to learn earlier time, the LRFD, the different risk level you take, and earlier AWS has recommended, instead of giving the probability of non-failure or probability of failure, they have just defined as level 1, level 2, and you could apply. Because of the uncertainties involved in this method, basically trying to use the 100-year storm condition representative of the fatigue, and this hotspot stress allowable is not representative of the actual joint, but it is coming from some empirical formula, because none of the design parameters are involved here. You can see here is basically the water depth, and your allowable stress is straight away coming from this type of graph. It is not recommended to use this method for detailed design, basically means for implementation purpose, but this can be used for screening purpose. For example, when you start to look at a jacket or a structure that is in the very initial stage, you do not have enough time, maybe you could use this as just a starting point. But then in the previous revision of API, this was actually there, but in the recent API they have removed from the mandatory section, but put as a guidance section in the later part. So, that means you can still use it at your own risk, but not recommended as a even for preliminary studies. So, you have to be little bit careful. Now, it is not, it is becoming as just the guidance notes at the tail end of the code. So, you have to be little bit careful, because this method is little bit crude, I would say. In association with this, they also have recommended a stress concentration formula, which is very simple. You will see this is one page covering almost all joints and basically all possible load types. So, you have TKY and X joints, as well as axial load, in plane and out of plane bending. All cases are given there, and this also is very much coming from very early works like 1970s preliminary works on the stress concentration, and that is why the formulas look so very simple and can be used very quickly. Whereas, when we are going to do a real design, this is not the formula we are going to use it, because the recommendations later like 1990s and the recent studies have done a lot of work, and the empirical formulas for SCF is slightly different. Now, you look at here, for example, axial load lambda times A. A is defined as a parameter relating your gamma and tau. I think gamma is, what is the ratio gamma? Gamma is d by 2t. Tau is the ratio of the thickness of the brace to thickness of cord, and basically lambda is defined as the value given here. So, as long as you have the values of gamma and tau, you can calculate the stress concentration in the axial direction, and is lambda times alpha. And then for bending in plane and out of plane, you have got 2 by 3 and 3 by 2 multiplied by A, as long as you can calculate the A. So, this is for the cord, that means on the peripheral points on the bigger member, and for the brace side you can see here similar formula, except that the brace SCF is dependent on cord SCF, you can see here. So, unless you calculate the cord SCF, you cannot come and calculate the brace SCF. Brace SCF is basically 1 plus something coming from the second term and must be greater than 1.8. That is the the idea behind the earlier studies on SCF. So, this is called simplified or basically the early studies of stress concentration, and we will see later these equations have been modified substantially. So, you will see that this procedure is quite simple. You do not really need to look at number of cycles, you do not need to look at the stress history over a period of time. What you are looking at as a design sea state, calculate the stresses, calculate the simple stress concentration factors using the simplified formulas, obtain the peak hotspot stress, and then compare that with the allowable hotspot stress as proposed in the API for level 1, level 2 for different water depths 40 and 100. And then for the detailed design methods, there are two methods distinctively we can identify, which is what is going to be used in the real practice. Of course, the left side one we have discussed enough on the fracture mechanics method, which I think we have derived the formula which is relating number of cycles to the initial crack growth from AI to AF. So, these two has been related, and we got a relationship which is defining cycles stress range with some constant, So, n times s to the power m is equal to some constant. That means, you have a various combination of cycles and stresses for a same answer, is not it. So, that is why you get a graph something like this. So, we are going to see this fracture mechanics is a starting point where the relationship between the number of cycles and the stresses were related, but unfortunately because of the complexity this method of fracture mechanics was unable to proceed for the detailed design or the initial design, and basically because of the informations not available. So, using the same method we try to do alternate scheme wherein we will use the relationship between the stresses and the number of cycles to failure, but we will not actually go and investigate the crack growth, but we will look at the safety of the joint in a slightly different manner. So, what exactly is the idea? The idea is based on so called the stress and number of cycles to failure relationship for each of the material, each of the type of joint that somebody has generated. So, what has been done, again we have gone back to from theoretical background, we are unable to proceed, we go back to experimental studies, fabricate a joint, go to the testing machine and make it to fail, note down the number of cycles at which it is failing and find out what was the applied stress range. So, repeat this for several times until you get reasonable data that represent various ranges of cycles, various ranges of, that means you will fabricate say maybe 10 or 20 models if you have time, if you have money. But the problem is such test takes long time. Cyclic test does not mean that you can finish the testing in half a day, because you need to apply the number of cycles as per the reality. So, that means it will take a longer time. So, doing too many tests is not a feasible idea. So, what people have done in the earlier time, they do few tests, calibrate with the numerical models and then use those data to extrapolate. So, it is not that every time they do 20 and several tests, because it is involving time and money. So, this SN curve is a methodology to establish the relationship between the number of cycles to failure for a particular given stress range. So, if you establish this, then basically next time you can go and find out for a given stress range what will be the number of cycles that we can allow, because that is the idea behind. So, this SN is a relationship derived experimentally incorporating few things. One is the geometry, material and some geometric effects. For example, when you fabricate a weld, I will show you some photographs. I just picked up from yesterday, what is behind, something like this. I think the other day, hope you are able to see, you could see here the surface of the weld is not that smooth. You will see that kind of profiles. Whenever the last weld bead is joining the material, you will see a sudden jump, some slope will be there. So, basically incorporating these effects, because when you are fabricating this, joint for model testing, you will include this weld effects, any undercuts basically at the location of the junction between the parent material and the weld, you may see that some kind of undercut or maybe a defect all those things will be incorporated in the SN, because incorporating these 3 in the stress concentration factors will be very difficult, even by experiment or by numerical models. So, the SN curve includes geometry, material and the defects due to fabrication. That means, either can be an undercut or profiling of the weld and any imperfections. So, that means, this SN method is obviously very good, because it represents the reality. We fabricate a typical joint of that type. It can be a plated joint, then you will have a different relationship. But only problem is little bit of hypothetical idea, because we are unable to link this failure number of cycles to the actual crack, because we are not estimating that. We leave that crack growth on one side. We will just decide based on number of cycles that we can allow and number of cycles that is actually applied from the C state. So, you compare like allowable stress versus applied stress. What we are going to look at here is, so many number of cycles of stress is applied, and we know that this joint will fail if you apply n number of cycles. So, the ratio will tell you the allowable cycles versus applied cycles. If the ratio is less than 1, then always the joint is safe. But unfortunately, what happened, either of them, either the allowable cycles or the applied cycle does not reveal what will be the crack on the joint. So, that is why we have a little bit of confusion there, maybe a hypothetical idea, but representatively we decide that joint is safe. And this method is in fact has been successfully used for so many decades. In fact, this is the only method that has been employed for the last 30-40 years in the design of either fixed structures or floating structures or mobile units, and still we believe that this method is representing the actual situation, and basically no other choice. Because of this, idea is little bit hypothetical. Uncertainties involved in the relationship between allowable cycles to the crack is very high. So, that means we may have to apply a larger factor of safety. So, in this method we apply reasonable factor safety to be decided by the designer. Of course, now the API recommends some numbers. For example, when you divide the applied cycles to allowable cycles, you get a ratio less than 1. If the ratio is equal to 1, then it is almost near failure. Now, you divide by the factor of safety. If your factor of safety is 2, then the ratio must be less than 0.5, isn't it? So, as long as your ratio of fraction is less than 0.5, you have a factor of safety of 2. If you have a factor of safety of 10, then the ratio must be less than 0.1. So, that is the idea behind. So, this cumulative fatigue damage method is nothing but you take each C state. For example, you have 3 wave heights in the field, just forget about so many numbers. Take the first wave height, find out the stresses, find out the number of cycles that particular wave height is applied, because you can go and measure this information from the site, and correspondingly you find out what is the number of allowable cycles for that C state, and then find out the ratio. So, n1 divided by n1, and second C state do exactly the same thing and add it. The idea behind is the effect is cumulative, that is why we call it cumulative damage method, nothing but the effect is added as much the information like the wave is coming the next day. So, every time the damage is cumulatively added, very similar to what we learned last few classes. The crack is initially few millimeter and start to propagate, it is not closing up, it is adding the effect together. So, it is exactly similar idea, only thing is the representation is given by not the crack width or crack length, it is given by the number of cycles of load applied. Of course, having said the disadvantages of this method, the advantages are very good. The method is very simple, you do really no need to spend too much of your computational time, because it is basically a arithmetic, I would say. The whole method is arithmetic, as long as you have the stresses calculated on the structure and simply take the number of cycles applied over allowable cycles. We will see this method in more detail. Basically, what we really require in order for this method to work is the wave climate. So, wave climate is nothing but the relationship between the wave height and wave period and wave direction for a particular site at the for the duration of design life of the structure. So, if your design life of the structure is 25 years, you need information relating these 3 parameters for a reasonable period of time, because you are going to design the structure for future, not for the past. You might have collected the data for the last several years, then you need to extrapolate or predict what could be the potential distribution over the design life. So, this is where little bit of difficulty comes, because you have to actually get this prediction correct, otherwise all your calculations are not going to be correct. So, the wave climate is basically the description of your sea state conditions, either short term or long term. The next one is the structural response, which is very easy, because all of you are civil engineers, you can calculate the stress applied on a structure by means of static or dynamic analysis, which is very easy. As long as you know what is the sea state, you apply the loads to the structure, you get the response. Now, the structural response, you could include or neglect the dynamic effects depending on whether the structure is close to the natural period, close to the waves periods. That I think is a secondary matter, but most of the jacket structures are away from the natural periods close to the sea state conditions. Now, the wave scatter data can be described in several ways. One of the particular and the easier way is describing by the individual wave heights, which I think in the early days of this course we were talking about design methods. So, either the spectral method or the discrete wave height method we were talking about. The discrete wave height method, we take the individual maximum wave heights, and basically that means when you look at a histogram of sea condition, you look at each wave height and take that as the representative, or you could represent that sea state by means of a spectra of any type that we could specify for the particular site, but described by a significant wave height and a peak period. I think this is what you might have studied in your hydrodynamics. The spectral distribution is normally represented by significant wave height and peak period, whereas the time history is defined by wave heights and associated zero crossing period. All of you know what is zero crossing period, no? If you draw the time history, the period between the zero crossing to the next one, whereas the peak period is basically a relationship between the H max T max and the T jet. You will be able to calculate using the spectral distribution. So, there are 2 ways of doing it. We normally use the first one for simplified fatigue, basically using the deterministic analysis, whereas the spectral response will use the significant wave height and the corresponding peak period. Let us learn how much easy is to do this method first, then we will go to the response by spectral. In doing so, there are several things you need to work out. First means the structural response in terms of nominal stress, that means a simple static analysis of the structure for a given wave height, and stress concentration factors. Basically, we saw some simple formulas earlier, but you will see a little bit complex formula. Then hotspot stress range is the multiplication of the local stress multiplied by the stress concentration factor, and the SN curve is the relationship between the stress that can be applied to a structure until failure, with number of cycles being n. And then the cumulative fatigue damage is nothing but the added effect of the ratios of applied cycles to the allowable cycles, and the factor of safety is basically defined as how much additional safety margin you want to keep on the fatigue damage. So, if you want to have a safety margin of 10, the fatigue damage must be restricted to 0.1. If the safety margin is 1, then the damage can be as much as 1. So, that is the idea behind. So, these are some of the definitions, you must keep it. Nominal stress range is nothing but the stress applied to the structure slightly away from the joint, is not it. For example, if you have a T joint, the joint is here, the member is subjected to a stress of some magnitude, but the range is nothing but the positive, negative or the maximum, minimum, the difference between the values of these two will give you the stress range. You must remember it is not only the amplitude, you should go and look for the positive negative amplitude or min max amplitudes, and then the difference could give you the stress range. Stress concentration factor is basically the local or localized increase at the junction between the brace and card. So, you need to calculate this. Of course, this is the ratio of the local hotspot stress to the nominal stress applied elsewhere slightly away, and then when you multiply these two, this with this, you will get the hotspot. Hotspot is nothing but the localized increased stress, which we are trying to find out by indirect means, because we know how to calculate this, by empirical methods, then we try to get this. But of course, there is a easy way. You do not want to do both of them. If you want to do this one straight away, of course, yes, it can be done. You can do a finite element analysis, you can find out, but not every time you have the time and resources to do the finite element analysis. That is why we try to do this, and we do this by empirical means and try to obtain this indirectly. So, that is the idea behind. You could ask, why should we do this? We have big computers, we can do this hotspot stresses ourselves without relying on either the stress concentration factor given by some people in the empirical formulas and the nominal stress, which could be done in some cases. If you have a problem which is so complicated, you could actually carry out FE studies yourself, find out the stress concentration, as long as your FE studies are correct, because several times what happens, FE studies are done incorrectly, then you will not be able to get the information correctly. Of course, the SN curve is not something that we want to generate, which is time consuming, involves a lot of money. So, basically we have to rely on the SN curve generated by the agencies like codes and standards or institutions governing the country. They have already done that exercise, every country have got. So, basically you could use that information without much worry. So, once you have this, then you can go and calculate the fatigue damage. So, wave scatter data, we have two parameters, basically the wave height and the wave period, which can be described by the maximum wave height for individual wave and the corresponding zero crossing period. And basically the data will look something like this. If you look at this on the left side, you see here the vertical axis defining the wave height, the horizontal axis defining the zero crossing period. Each of the bin is describing, for example, this is basically, this vertical line is 2, this vertical line is 3. That means, between a period of 2 and 3 for a wave height of 0.5 meter, we have number of occurrences 307. The idea is each one is given a range, it is not a specific or a discrete item, it is just the bin covering certain range of wave height, certain range of wave period. So, how do we get this? So, if you have a time history recorded at a site, for example, you will have to go and analyze the data to find out individual wave height typically and account it inside this bin, as long as you satisfy this condition, as long as the period is within 2 and 3 and the height is less than 0.5, that means 0 to 0.5, then you will count them inside this bin, and if it is, say for example, going to 0.5 to 1 meter, you will come down, count them in the second bin. So, you have to do this for the whole range of data that you have. So, every time when the wave comes inside, you will do this. So, this data, how do we get it? The only way to get this is to have a site specific measurement. That means, you will deploy a wave measuring devices at the site and then record the variation of sea state, the variation of surface elevation, and analyze the data, and basically you will get this information, and this is where the most difficult part. Now, you want to plan to build a platform in a particular site, but that is in future. So, what we are actually measuring is the past. Now, we need to make sure that the measurement that you are doing for the last 1 year is going to be representative of the next 25 years, is not it? Because you may not actually have 25 years measurement. Nobody is going to plan for a 25 years measurement thinking that after 25 years there is going to be a platform there. So, normally when you identify a field which is potentially having oil and gas, probably you will be planning to do a survey for a shorter duration, 3 months, 6 months, maybe 1 year, but not more than that. So, you have a measured data for 1 year, but then you are going to rely this for the next 25 years or next 50 years, and this is where the difficulty. Of course, number of mathematical models have been developed over the long period of time, which is going to describe based on the information that you have collected, that what could be used for next few years. So, there will be a correction required for this data, which is only 1 year measurement, but then you are going to use for so many years of your design. So, this is where you will see there is a uncertainty there. Whatever the mathematical models we are trying to do is impossible to predict what could be the number of occurrences that will occur the next year and the year after. But typically, leaving behind the uncertainty, a particular C condition at a location can be described by a simple 2 parameter, wave height on one side and the wave period on the other side, and numbers indicating number of times they occur. Now, if you look at it, the whole C state has been covered here. Each time a wave height and a wave period is associated with number of cycles, basically the energy in the C condition, and the larger the number, for example, if you go around, you look at it, 6,000 is the biggest number. So, what you see from here, 2 meter wave height with wave period ranging from 4 to 5 is predominantly occurring at that site, 6,000 out of probably few 100,000. So, basically that is the largest number that you can see. That means, if you go to the site, every time you will see very often the wave height is around 2 meters. So, that is the idea behind it. For example, if you do not have any of this number, if you see just only one number in the whole scatter data, that means that site is very good. You do not need to do measurement, because basically only one wave height, one wave period, and all the time it occurs. You will not find a place like this. So, basically that is the idea behind this wave scatter data, is the scattering of the energy from lower C state to a higher C state with a mean value, or the center of the highest occurrence is somewhere. So, from here what we can understand, if you do a weighted average calculation, most of you might have studied in your mechanics to find out the center of gravity. You can find out very easily by multiplying the area times the center of gravity of individual. Similar thing you can do it, you can find out where will be the maximum energy content, basically multiplying the wave height and the number of occurrences. You will see that typically will come around 4 to 5, somewhere here. If I just look at it myself without even doing calculation, I can say the effective wave height could be somewhere between 2 to 3 meter, and basically the wave period could be 5 to 6 seconds, somewhere there, because I know the numbers look in that order. Even if you do calculation, you will be able to come to conclusions, basically somewhere here. What it means, 5 to 6 seconds. So, imagine you take 1 year, which is 365 times 24 times 60 by 60 divided by, say, divide by 5 seconds. How many cycles you will get? Nearly 4 million cycles, 3.5 to 4 million cycles. So, you can see, if you have a C state condition at a particular place for 1 year, with every time some wave is crossing, you will see that few million cycles are going to occur, but you may not have the 100% every time C is rough, sometime maybe calm C conditions may be there. So, basically will be around 2.5 to 3 million cycles. So, for 1 year you are going to face 3 million cycles of some C state. It could be smaller, bigger, but in the nominal somewhere around 2 meter wave height. So, you could actually do that simple calculations. So, how do we do this? Basically, this 2 parameter, one information is missing, wave direction is missing, because now you have a structure which is constructed at the site, but what we do not know is which direction wave is coming, because our structure is sensitive to the direction from where the wave is going to come. So, what we normally do is we need to actually measure the information at the site, predominant direction of wave every particular duration, but most of the modern wave measuring devices actually can get this information as a second parameter during the recording itself. but if you do not have, normally what we do is we collect the information with regards to wind data at the site. You have a windrows diagram. I think most of you might have seen the windrows diagram, no? The diagram indicating the periodical or the seasonal variation of the direction of wind with respect to the horizontal direction. So, you could get that information, because mostly these waves what we are looking at is the locally generated or wind generated waves what we are looking at, and basically you could use the information from the windrows diagram to relate to the waves that may occur. And sometimes we do use this, because the earlier, like say 10-15 years back, measurements devices for wave heights, they do not give you the direction. We used to have lot of difficulties, and basically you have the wave data and we have the wind data, and with the wind data you just decide to do certain ranges. For example, the waves are going to not only just come only on the direction what I have drawn here, you may have any direction, but what we have decided is the band of the area. For example, 0 to 30 degrees, if it occurs, I will assign to one direction, because theoretically speaking you should do the analysis of the structure for all possible wave directions theoretically. That means you may have thousands and thousands of directions, you may not actually practically possible. That is why we actually cumulatively find out, for example, any wave direction between this point to this point added to this direction, that means it is represented by one particular direction, rather than I will do an analysis for every direction that I would encounter at site, because this is to simplify the design calculations. Otherwise, you will end up too many number of variables and too many number of wave directions, we cannot actually do it. So, basically in the earlier days, I think we have studied for a typical jacket structure how many directions we require, minimum 8 directions to represent the weak or the maximum stress producing direction, which is going to be a important parameter. So, normally for typical rectangular structures, API recommends minimum 8, I think it is a common sense, but if you have a tubular structure, for example, single column, does not matter, you need only one direction, because any direction you apply, for example, circular tube, any direction you apply will be same stresses, whereas for rectangular or square structures with the structural frame arranged in this way, you need to have to identify the weakest direction by which the stresses will be maximum. So, by inspection most of the rectangular frame structures, if you apply 8 directions, you will be covering most of the cases. So, typical distribution you see here on the bottom, there is a table, you can see here we have picked up this type of directions, which as a designer we know this is the direction going to cause maximum stresses, and to get this, for example, 22.5 degrees, let me go to 22.5 degrees, somewhere here I got only 0.1% of the total waves approaching from there. That means, this is any wave approaching from 0 degree up to 30 or 40 degrees has been lumped into here. You understand the idea, no, how the directions were arrived. Any waves approaching from 0 to 40 is assigned as a 22 degrees, very similar like this. Any waves having 3 and 4 seconds in between is assigned as that particular number of occurrences. So, what we are looking at is the kind of approximation just to reduce the amount of work that we need to do. Strictly speaking, you actually have to do analysis for each one of the wave. If you do not want to do any of these approximation, you can pick up one wave, analysis results, and go to second wave. That means you will do the analysis for millions of waves, which we do not have the resources and time. That is why we are condensing our data, that any wave coming between 3 and 4 seconds as the period, we just put it, so that we do not need to do as many analysis as we require, but we can do simplified. So, basically this method is an approximation to the real sea condition, is not it? We are just trying to condense the information to our easy and way of doing calculations. Actually, the method is highly susceptible to error depending on who is doing the analysis. For example, I have come up with 2 to 3 seconds as my band or my division. If I go to another person, he decides to do 2 to 4 seconds as the band. So, what happens? The approximation becomes more. If you go to another person, he can do between 2 and 2.5 as the band. So, the accuracy increases. So, that is where the problem here, there is no mandatory information available from the codes that what should be the division that you should look. Strictly speaking, you should not divide, you just take each wave and then go and do it, which is not feasible. So, highly depends on the particular designer that who is doing this analysis. That is why you have to be careful that this method may lead to conservative result or may can lead to unconservative result depending on the particular designer. So, the same data can be described in a generic form instead of information like this. Basically, the wave heights are divided into bands from 0 to whatever the maximum wave height at that particular site. Similarly, the wave periods can be divided into 0 to the highest period possible there, and to be filled with information that is corresponding to each of the band, and the total numbers occurring at the site could be either added vertically or horizontally, you should get the same information. So, typically 2 parameter wave scatter data is nothing but the occurrence data for each of the siege conditions that is existing at the site. Some of the areas could be empty, does not mean that every one of them will have some numbers. Like if you see this table, what is the meaning of this, that there is no information there, that means that siege state does not occur or arise at the location. Basically, for example, you go to 5 meter wave height with a wave period between 2 and 3 does not exist and cannot exist. You can go back to your wave theory. Some of the combinations of wave periods and wave heights cannot exist because either they cannot be generated or they cannot be propagated to the site because it might have already broken. So, basically you see wherever the data is not available, that means they does not exist, you cannot go and assign the number. Basically this is a generic table that you would like to generate. The reason why I wanted to show this is basically the next will be the important information, in the information containing the directions with respect to wave height. Sometime you get this information from the measured data. You have 3 parameters, 2 parameters are already linked. The third parameter, which is wave height with the direction, is linked by again the number of occurrences. That means, when you have a time history measured, you can get this information from the measured data. So, from here the number of occurrences also same. The relationship between the wave period and the wave height is n number of occurrences with the division something like this. The same waves, because you are looking at the same wave in a different combination, you have the wave heights and the wave directions. Also when you sum up, it should get, because you can't have 2 different numbers. Now, using this data you can actually link the direction with the wave period, because you got 2 linkages, just multiplications. Most of the projects we get these 2 tables provided by the previously measured data from the wave height measuring devices. And basically the reason why we need is, you can multiply this with the ratio of this to this to get the corresponding directional distribution. So, basically that is the reason why we need these 2 tables. And sometimes the owner themselves generate this data for each direction. For example, this particular project, they have already done that exercise what we wanted to do, describing the wave height versus the period. With each direction the numbers are provided. So, once you get this type of data, then we do not have much to bother to generate, because for each of the directions they have already given like 8 tables. Each direction is provided with the wave number of occurrences, wave period and wave height.